Welcome, everybody. Thank you for joining us today. My name is Romina Pesoli, and I'm part of the research team at the Applied Polymer Technology Gateway at the Technological University of the Shannon Midlands Midwest. We, together with supercritical fluid processing with Siobhan Matthews here in the panel, and the European Medical Polymer Division of SPE, we are very happy to bring you the first of our webinar series in trends in polymer processing and investigations. Each month, we will bring a polymer expert to talk about the latest advances in polymer characterization, manufacturing, and processing techniques. I remind all the participants and attendees that the microphones are mute, and if you have any questions, please send them through the question and answer box. Today, we welcome our first speaker, Fred Jaubert. He is the Technical Director of Dynisco. He has a background in chemistry and engineering, and over 28 years of experience supporting technical support for polymer processors across Europe. Today in his talk, he will show us the technology, the applications and benefits of rheology in a production environment. Thank you, Fred.
Thank you, Romina. So I'm going to take the lead for the presentation. Yeah, as you said, I'm working for 30 years in the plastic industry with Dynisco. Just to present briefly Dynisco. Dynisco is a leading manufacturer of melt pressure sensor, mainly for the extrusion industry. And Dynisco is doing sensors for about 70 years now. And we acquired about 35 years ago 2 companies dealing with rheology and the measurement of viscosity of polymers. One was a company called Keynes, who is doing lab instruments. Another one was called SayScore, and they were doing online instruments. And these two brands we have developed under the hood of Dynisco. Today, I'm going to talk on the few instruments we have to measure viscosity on plastics and polymers. First one is a melt flow indexer. We are just going to see it briefly. I will emphasize my presentation today on the capillary rheometer, because this is also an equipment that you have at the university and you can serve customers using this instrument. And I will briefly talk about what we can do online and the idea of bringing all these type of measurements together to get a better picture of the production of polymers. So first of all, the melt flow indexer, or it's called also melt flow rate tester. It's where we are getting a result which is called the MFR, or melt flow index, MFI. The principle of the instrument is pretty simple. You have basically a barrel which is heated at a standard temperature, which is given by the standards. And you have a capillary die, which is at the bottom. You put the sample of material in between, you heat it up, and you have a piston and a weight. And basically, you are pushing the material through a capillary die and measuring the throughput in grams per 10 minutes. That's a very, very basic and raw measurement, which is made by a lot of plastic manufacturers to check their incoming material or when they are doing recycling. So as I said, the applications of the melt flow indexer, we call it LMI in Dynisco, is to check incoming material before to process it. This is really applying to all type of industries. Could be extrusion, injection molding is also quite a big portion of users of melt flow indexers, because we are getting material in silos, and you need to check the material before you put it in the silo. Also, it's used by recycling companies or compounders or resin manufacturers to be able to provide the specification of the product they are going to sell to end users. And finally, it's the first instrument which is used in research and development for quick testing of the behavior of a plastic and the flow of polymer. So the second instrument where I'm going to emphasize my talk is really what is called the capillary rheometer. Capillary rheometer is I would say, the big brother of a melt indexer. It is a similar process as a melt indexer. So you still have a barrel which is heated at a certain temperature, but it's much more flexible. The standard which is used for the capillary rheometer is not really imposing you a specific temperature, load, and so on. You can really do whatever you want with it, and we will see later results we can obtain for it. And so basically you have also a capillary, but the capillary also is flexible. And instead of putting a load on the top of a piston to push the material through the capillary, we have really a motor, and we are really applying a force or what is called a shear rate, which is much stronger than what you can get with a melt flow indexer. In this case, we are not measuring the flow by really the throughput of material and weighing a sample of material. We are using a load cell or a pressure sensor to be able to measure the force which is applied to the polymer through the capillary. And of course, we have usually a computer system attached with the software which is helping to make the analysis of the polymer at the end. So what is the advantage of the use of a different type of instruments based on your process of conversion? So if you are doing compression molding, for example, which is really a simple process, I would say, in sense of polymer viscosity, you can use a melt flow indexer. It's well used for this type of process. If you are doing extrusion, the melt flow index is still a valid measurement, but you are really at the border of the measurement with a melt flow indexer. And if you are doing injection molding, you have forces, so shear rates, which are much, much higher than in extrusion. And in this case, the melt flow indexer is absolutely not adapted. And this is where the capillary rheometer is really coming into play. You see also here the dynamic rheometer. Dynisco has a sister company called APT Technologies who is doing dynamic rheometers, where you can also make some viscosity measurements, which are slightly different from capillary rheometer, but you have some limitations in terms of temperature and the shear rate that you can apply. So basically, you have to play a little more with testing conditions. So again, what are we doing with a capillary rheometer? We are measuring the melt viscosity of a polymer. So basically, as I was showing earlier, we are simulating exactly the same process conversion, especially as injection molding. Injection molding, first, you have a screw, of course, which is there to mix the polymer, but then the second step is really to push the polymer through a nozzle and through channels into the mold, which is pretty similar to what you do when you are pushing the material through the capillary die of a capillary rheometer. So the principle of the measurements are made of the rate of flow, so versus the force. So the rate of flow is the shear rate, and the force will be converted to the viscosity of the product. You have two modes of operations to run the capillary rheometers. One is called the rate sweep. Basically, what you are going to do is that you are going to vary the speed of the motor. So you are going to vary the shear rate, and then you are going to measure the range of shear stress and viscosity over the range of shear rates. And the second possibility with this instrument is, instead of running with various shear rates, you can run the same shear rate over a period of time, and you can also do pauses in between, and then you will be able to measure what is called the thermal stability of a polymer. First of all, what we call the rate sweep or shear sweep test is the test where we are going to vary the shear rate. So the polymer is melted into the rheometer, and this is done at constant temperature. In a capillary rheometer, you cannot really change the temperature during a test. You can make tests at different temperatures, but for one test, you can only run at one temperature. And what we are going to do is we are going to give constant speed through on the piston, and this will generate a constant flow through the capillary. And we are going to measure this force or this pressure that we need to generate to be able to be at a constant flow. And then once we have a stable measurement, we will stop and we will go to the next measurement. So basically, in one test, we will do several different shear rates. And so it's different speeds of a piston to measure different viscosities of a polymer, depending on the force which is applied on it. So then I have collected some various viscosity curves of various polymers, just to show you what we can get from a capillary rheometer. So you see, every time we have applied different shear rates, and of course, depending on the shear rate, you'll get a different viscosity of plastics, of polymers. When you are running plastics, I would say, not elastomers, usually we are running the test by starting with a fast speed first and then going down to the lower speed. If we are running elastomers, usually we do it the other way around. So we start with the first points, which are here, and going down in viscosity. If I show you this, it's just so that you can see the magnitude of the viscosity we have on the commodity resins and the shear rates we are generating compared to what we get with what we call more engineering resins. Here we are at 1,000 Pascal seconds, while when you are running the same type of testing on very more engineering thermoplastics, you see that we are going a little higher. And in fact, I mean, we need to extrapolate this curve, so we have much more higher viscosities in this product than what we get with more commodity resins. And now, why are we checking this viscosity, and what is the use of this viscosity curves? The thing is, this is if you plot various viscosity curves of the same polymer, you will see that they are not always matching together. So you will have some differences. So as you see on this graph, basically depending on, for example, the molecular weight, if the molecular weight is increasing, then the curve will be higher. This seems obvious because if you increase the molecular weight, the product is more viscous, so you are going higher. And you will see also with fillers that it will go up. And of course, if you increase the temperature, the viscosity will go down. Also, if you put plasticizers or lubricants, it will go down. What the capillary rheometer will help you is to define what will be the consequence of what you are changing on your polymers. Also, we can be able to see, for example, moisture, residual monomers in the product. Moisture is really critical, especially if you think of PET, for example, polyester terephthalate, or if you think also of polyamides. The second type of test we can run is called the time sweep test. So basically, our stabilization test, where we are running at a constant temperature and a constant shear rate. So we are doing, in this case, measurements at fixed interval during a predetermined period of time. So we are making a test, stopping the instrument, then starting the piston again, and then taking a second measurement, and so on every minute, or every 5 minutes, 10 minutes. And depending on what the curve is going to do, we will see if we have thermal degradation or if we have cross-linking into polymers. So this is just another way to show it. So basically, with time and temperature, you can get either degradation or cross-linking. And the result on the viscosity curve will be like this. So if you have cross-linking, the viscosity is going to increase. If you have degradation, it's going to decrease, obviously. And if you have a stable product, you should not see any noticeable variation of the viscosity over time. This is, for example, what we can see. This test has been run on a nylon 6.6, which has been running every time at during 35 minutes at various temperatures, starting from 280 and 315. And we see obviously that the higher the temperature, of course, the faster the degradation of the product. So as I was mentioning, the applications of a capillary rheometer is the measurement of the apparent viscosity versus the shear rate. It's helping to determine the fit of a material with a function, what you really want to, what you are really expecting from your polymer. It's also used as research and development purpose. What is not mentioned in this presentation is a lot of software used to do a modelization of a flow in extrusion dies or in molds are also using some key parameters that are determined using a capillary rheometers. Like software like mold flow and so on, they need some specific values, and we can get them from our software and with our capillary rheometer. But the last application I wanted to discuss is something which is slightly different, but we can also use it, especially when you are running then measurement online, is what is called activation energy. The activation energy is needed if you are doing, for example, a melt index or a viscosity measurement at a different temperature than the temperature you would like to have a result. Let's say, for example, this is also the topic of the next slide. If you are running a system online and you want to measure polypropylene, the standard test for example, for melt index or viscosity for polypropylene is 230 degrees C. But on the extrusion line, maybe you are going to run at 260 or 270 degrees C. Using the activation energy, it will allow us to be able to recalculate the value expected at 230, even if you are measuring it at 280 degrees C or 270. And one example of this is what we have developed is a product which is called Dynisco Indicator, which is an online LMI LCR. The process of operation is slightly different in this case, but it's still pretty close to what we use in a capillary rheometer. Instead of having a piston which is pushing the material through a capillary, as you see here, we have a gear pump which is going to depending on the speed, to generate a flow of polymer and an increased pressure. And for example, if we are applying a constant speed and measuring the pressure on the pressure sensor, we will be able to calculate the viscosity of the product. On the contrary, if we run at a constant pressure and varying the speed of a gear pump, we will be able to directly determine the melt flow index of a product online. And so as I was mentioning, for the application of VPI, it's continuous measurements. You don't have any operator interventions. It can be used in recycling and compounding for quality control, and it could be linked also to the melt flow index or melt flow indexer and the test which is run in the lab. We are also using it for the measurement of IV online on recycling line. And basically, this is exactly what I'm doing today. I'm at the customer to do this. So this is, I think, probably the next step for a lot of companies to go to online measurement. And last slide. I hope I've not been too long and too boring. We have also now started to build what we call an industry 4.0. Basically, we can collect the results of legacy instruments, old melt flow indexers, old capillary rheometers, and also a new lab instruments, and also link them through a cloud to the measurements that we can do online. So basically, it means that, for example, we can run our Dynisco indicator online and run a capillary rheometer test every 8 hours, for example, and we can then match and check that the measurement which is given online is really confirmed by the measurement in the lab for a better and more accurate production follow-up.
Thank you so much, Fred, for that. We'll start now the question and answer. We have a few questions already in.
I've not seen it because I was on full screen.
That's great. I'll read them aloud so everybody can hear them. So which is better, a low cell or pressure transducer, or are both required for successful measurement?
It really depends on what you want to measure. I mean, we prefer to use, I prefer personally to use a pressure sensor to make the measurement on a capillary rheometer. But when you are really on the low shear rate, you have to think that the accuracy of a pressure sensor is based on this pressure range. So you need a very low pressure range sensor to be able to measure accurately the values of viscosity at low shear rate, while a load cell is much more accurate. At the same time, the load cell is also affected by the friction of a piston. So this could also be sometimes an issue, but usually at low shear rates, the friction of a piston is not so much.
Great, thank you. Can the online viscosity measurer be used only in extrusion?
Yes, yes, only in extrusion. We really need to have a constant flow of a product. It cannot be a cycle measurement.
Okay. Is the Bagley correction required when pressing material from a bigger reservoir into the smaller die, or is it built into the software?
Well, the Bagley correction is available. It's not required. The Bagley correction is really to measure the entrance effect at the die. And it is built in the software. So if you need to do a Bagley correction on our instrument, it's possible. You will need to have at least two different capillaries with two different diameter, the same diameter and different L/D ratios, so different lengths, to be able to determine the viscosity, the corrected viscosity with Bagley correction.
Okay.
Most of customers are not running Bagley, usually. Okay. On at least on quality control.
Okay. How to do testing online? Does it based on modeling? Not sure.
I'm not sure about.
No, yeah. I think the question is the testing online is based on sort of modeling. Maybe it's the person
it's absolutely not. It's actually not modeling. It's really a capillary. And of course, I mean, we are converting a pressure to a force, but that's it. I mean, for example, if you run a standard capillary die and you want to measure the melt flow index, you know that the pressure in our instrument will be 43.2 psi, or about 3 bar, and that's not really a model. I mean, it's a calculation, but it's pretty straightforward and very close to the measurement you are doing on a capillary rheometer anyway.
Yeah, great. In terms of degradation in time sweep mode, how do you conclude that it is degradation? Because without any reserve test, how can be sure about degradation? Maybe it is just rate of unentanglement of chains?
Oh, I'm sorry, this question is too technical for me. I don't want to.
Yeah, I guess I may take this one. Yeah, like of course, in some levels, if there's a decrease in the viscosity, it could be another process that is happening in the background, but it is presumed then there is degradation as well, and it could be easily verified. Which type of test will you use the capillary rheometer for incoming material inspection, and what will be the benefit?
So the first test for incoming, as I was mentioning, is more of a melt flow index test. It's the easiest one to run, but you can also run a capillary rheometer test. And we have developed, I wanted to show the slide, but I did not make it for this presentation. We have on our instrument a quality control module where basically you can just run the test, and based on the history of some good samples you have been running in the past, you can create what is called a viscosity tube, and you just load this viscosity tube and the test you have just run, and you can immediately say, my product is good or not good as incoming test. So it's a very simple test, but I think you have been running our capillary rheometer. The instrument is quite easy to operate, and I would say even even basic operators could just run this test and be able to determine very quickly if a material is good in terms of quality control or not.
Okay, great. I have another question here. In a visco indicator, is it possible to get elongational viscosity too?
No, not at this point. No, we have not made any development to measure the elongational viscosity.
Fred, and I have a question as well, if I may. I have gone through all the questions that I have. For the inline measurement, is this measurement have any sort of disruption of the melt flow or cause any problems with the flow of the final product? So let's say that you're adding it to a pipeline.
Not. As I said, today I'm just installing a system on a PET line, and the customer was asking me, and I was just calculating the flow we are using is about 1.4 kilograms per hour. So if you compare it to a line which is producing a ton an hour, I mean, it's really neglectable. It's not really going to affect the general production. No.
That's great. Is there any other questions from the floor?
Romina, I might like to ask Fred, I don't know if you can hear me, a question.
Yes.
Fred, can you explain how and where you would normally put the online rheometry on the extruder? And does it come offline, some of the material, as it's processing? And just what the general setup is for people, if you can tell us that.
Yeah. Well, so we are connecting the online instrument at the end of the extrusion line, usually just before the die, after the screen changer, obviously, because we don't want to have contamination in our instrument. And it's how can I say? I mean, it's just a connection on the side. I'm not sure exactly of the question. If you want to
I think a lot of people are interested in online rheometry and how it would work. How simple is it to put onto an extruder, say, for example? And then the measurements, they're real-time measurements. So there'll be good benefits. And can you then link that up to your machine to change some parameters, as you're processing?
So there are a lot of different applications. For example, we have right now an application at a customer who is doing polypropylene recycling, and they want to increase the melt index, so decrease the viscosity, and they are using peroxide to do this. And with our instrument, which is just connected at the end of extruder, we have been able to control the level of peroxide so that they can get quite a constant melt flow index at the end of the extruder. And for example, we were in a range of 42 melt index at plus or minus 2, which is much, much better than the customer was getting before, because before they had to take a sample manually every hour or every 2 hours, run a test, and then adjust the level of peroxide based on it. Now it's done automatically. And they want to equip all their lines with our instruments now, because it's much more easy for the operators and much more stable production.
Yeah, and that's great, because as you were talking, I remember years ago doing capillary rheometry, and we used to have a chart recorder waiting for, the curve to flatten out. And now it's fantastic that you have all of these applications, because it's online, it's real time, and you can change and adjust accordingly. So it's kind of moved from an MFI to checking materials, the same grade of materials when they arrive, to now actually checking them, how they perform in your extruder.
Exactly. Yep.
And then adjust as you're processing, so you're getting the best out of your materials. So the real thing also for me that's very interesting is the Internet of Things. So can you explain a little bit about how Dynisco has a vision for Internet of Things? So you've got the online rheometry, more and more people are putting that on. So how are you going to fit in the Internet of Things, for the next 5 years or something like that?
Well, our online instruments, so the last one, the visco indicator, is already fitted with an IoT system, Windows IoT. And we are using the cloud of Microsoft Azure, and we are uploading automatically the measurements, which are done online continuously to the cloud. And also our new melt indexer, the latest generation, is also fitted with the same type of Windows IoT system. So basically, every time you have a test which is run on the melt flow indexer, it's going to the cloud. And we are now trying to find a way to match the measurements which is done online with the lab instrument, so that when you take a sample during the production and you run it into the lab melt flow indexer, we can link it directly to the time the sample was taken from the visco indicator.
Great.
And so this will be really a total quality, because then, and the good thing also with the cloud is that the manager don't need to be at the plant to be able to check it, but he could also check it from home, or he could have some alerts that there is a problem, there is deviation in the production, or there is a problem with the instrument.
That's fascinating. That's very interesting. Fred, last question. Out of curiosity, really, which other polymers have you used with the online rheometer?
I've been using it right now on polyethylene, polypropylene, and PET.
Okay.
That's my experiences right now. I have now a second line running on PET. We have some on polypropylene, some on polyethylene, which are running great. Used different ways, as I said. For polypropylene, it's really adjusting peroxide. With polyethylene, it's really mixing different type of recycled products to be able to keep a constant melt flow index.
That's great. That's great. Well, thank you so much, Fred, for joining us today for this very interesting talk. And thank you for all the participants for joining us.
Thank you to all people to attend this meeting on this presentation.
Exactly.
And as I said, it was not really intended to be a real rheological and technical presentation. It's more just an opening on the rheology. And feel free to come back to Romina or to me or to Daryl with any additional questions. Absolutely.
Please, in the Eventbrite website where you registered, there's the LinkedIn of Fred LinkedIn, so you can link with him if you have further questions, as well as you can link with us through LinkedIn and Twitter.
Yeah. And as I mentioned already, if customers want to have some testing done on the capillary rheometer, they can just contact you, because you have an instrument in the house, so to be able to run testing.
Absolutely, that is right. Okay, thank you all, and see you next time.